Hello guys, welcome to my channel, and in this video I'll explain you article number 2.13, effect of dielectric on capacitance. In my previous video I explained you what is the capacitance of a parallel plate capacitor. Now we'll introduce a dielectric with some dielectric constant in between the plates of the capacitor, and we'll see how does the capacitance of the parallel plate capacitor changes. Okay, so let's start. With the understanding of the behavior of dielectric in an external field developed in section 2.10, let us see how the capacitance of a parallel plate capacitor is modified when a dielectric is present. Okay, and we have already seen that how does the dielectric modify itself when we place it in an electric field. Okay, that we've seen in section 2.10. You can check that video first if you haven't. Okay, as before, we have two large plate area of each of area capital A separated by a distance small d. The charge on the plate is plus minus q, corresponding to the charge density plus minus sigma, with sigma is equal to q by A, when there is vacuum between the plates. Okay, so as we have seen in the previous video, there are two charge plate of area A. Okay, and their distance between them, or the separation between them, is small d, and the charges on these two plates are plus q and minus q, and the surface charge density of these two plates is sigma and minus sigma. Okay, then what will be the, first of all, what will be the electric field between the two plates? We have found out electric field. We are denoting the electric field E naught. What does E naught means? When there is no dielectric between the two plates, we'll say this is the electric field between the plates when there is vacuum. Okay, so this will be sigma upon epsilon naught. We know from the infinite shear charge density derivation. Okay, for chapter number 1. Now moving further, and the potential difference V naught is equal to E naught times D. We know the relation between potential and electric field. Okay, so this will be V naught is equal to E naught times D. Next, the capacitance C naught in this case is, what is the formula? Capacitance Q upon V. Okay, so the capacitance for the parallel plate having air or vacuum in between the plates is Q upon V naught, and when we put the value of V naught, we'll get epsilon naught A by D, and this is the capacitance of the parallel plate when there is vacuum in between the plates. Okay, and this we have also seen in the previous video. Okay, so now we'll move to next and consider next a dielectric inserted between the plates fully occupying the intervening region. Okay, so now what we'll do, we'll introduce, so this is our two plates, and we'll introduce the dielectric which completely is immersed. Okay, which is completely inserted. Okay, completely fill the space between the two plates. Okay, the dielectric is polarized by the field, and as explained in section 2.10, the effect is equivalent to two charge sheet at the surface of the dielectric normal to the field with surface charge density sigma p and minus sigma p. Electric field in the dielectric then correspond to the case when the net surface charge density on the plate is plus minus sigma p, that is E is equal to sigma minus sigma p upon epsilon naught. So when there was no electric field, when there was no dielectric, then there was an electric field E naught. Okay, inside this capacitor plates. Okay, and this was because of sigma naught and minus sigma naught. When there was dielectric, then there was electric field induced because of the polarization. Okay, this is EP, I can say, induced electric field, and you see these two are in opposite direction. So what is the net electric field inside the dielectric now? So this is E, that is the net electric field is E naught minus EP, because they are in the opposite direction. Okay, so I can also say this it like that the net electric field inside the dielectric is because of a surface charge density sigma minus sigma p, because of a conductor having surface charge density sigma minus sigma p. Okay, I also say it like this. Okay, so now E is equal to sigma minus sigma p upon epsilon naught. So this is electric field inside the dielectric, so that the potential difference across the plate is V is equal to ED. Okay, so now you know what is potential difference. It is simply just multiply the distance between the plates by the electric field, so you'll get this. For linear dielectric, we expect sigma p to be proportional to E naught. Okay, now the polarization, the more is the electric field, external electric field, the more is the polarization we know. So this sigma p is proportional to E naught. okay, and that is 2 sigma. And what does the electric field proportional to? Sigma, because the more is the charges on the plate, more is the surface charge density on the capacitor plate, the more is this electric field. So we can say that this sigma minus sigma p is proportional to sigma, okay, because this is proportional to this and this is proportional to this. So this sigma minus sigma p is proportional to sigma. So now sigma minus sigma is proportional to sigma, okay, and when I remove the proportionality I'll get a constant, that is k, okay. So what does k tells me? That how much is the net charge, net surface charge density on the plates now to the surface charge density when there was no dielectric, okay. And now k is a constant of characteristic of the dielectric, clearly k is greater than 1. You see, k is what? Sigma upon sigma minus sigma p. Definitely the sigma will be greater, okay. This is the reduction in the surface charge density when polarization is there, okay. So definitely this is greater, so k is obviously greater than 1. We then have v is equal to epsilon sigma d upon epsilon k, okay. So now what we can do, we have the value of potential v from here, okay. V is equal to sigma minus sigma p upon epsilon naught d. So I can remove this, I can put the value of sigma minus sigma p is equal to sigma upon k. So when I put the value, I get v is equal to sigma upon k and d upon epsilon naught. This were there in the formula, okay. And now you see what I can do, I can put the value of sigma here, okay. So sigma becomes what? Q upon a. So sigma is q upon a, so I put the value here, so b become this. Now I can find the potential capacitance. What is capacitance? It is charge upon potential. I'll put the value of potential from here. So what I get, this is potential is q d a epsilon naught k, and again one q is there because of the formula of capacitance. Q get cancel out, the capacitance become what? Epsilon naught k capital A by d. If you compare this capacitance when there was no dielectric, it was simply sigma naught A by d, okay. With the introduction of capacitance, what happens? With the introduction of dielectric, the capacitance has increased by k times, and that is the dielectric constant, okay. So the product of sigma naught k is called the permittivity of the medium, okay. This is called the permittivity of the medium, okay. You know sigma, and we have also defined sigma r, okay. Sorry, epsilon naught r, epsilon r, that was epsilon upon epsilon naught relative permittivity, okay. That was the ratio of epsilon permittivity of the medium and permittivity of free space. So this is also equivalent to dielectric constant, this epsilon r, okay. From here, this is the permittivity of the medium is simply epsilon r relative permittivity times epsilon naught, or k times epsilon naught, okay. You can say how much times the permittivity, how much time the permittivity of the medium is more than the permittivity of free space, you can say from here, okay. The dimension ratio k is equal to epsilon upon epsilon naught is called the dielectric constant of the medium, okay. This is called the dielectric constant of the medium, very important term. Now it is clearly greater than 1. Obviously, you know, the permittivity of medium is always greater than permittivity of free space, okay. What is this epsilon? So epsilon permittivity is how much is the electric field reduced by the medium, how much the medium influence the electric field, okay. So this is k, and now from this I can, as I told you, c is what? When c naught was a epsilon naught upon d, and c is k a d epsilon upon d. When I divide this two, what I get? I'll get a. You can divide them, you can get k. So from here you can also see c is equal to k c naught. So you can say capacitance, okay, capacitance of the capacitor when dielectric is introduced, of dielectric constant k is introduced, is increased by k times, okay. So I can define dielectric constant from here, okay. So it is the ratio of the capacitance of the capacitor when dielectric is introduced to the ratio of the capacitor when no dielectric was introduced, okay. So the dielectric constant of a substance is the factor by which the capacitance increases from its vacuum value, okay. You can also say it like that, okay, how much times the capacitance increase when dielectric is introduced, that is dielectric constant, okay. Though we arrived at equation 2.54 for the case of a parallel plate capacitor, it holds good for any type of capacitor and can in fact be used in general as a definition of dielectric constant of substance. Okay, we only derive this for parallel plate, but it can be viewed for any other case or any other type of capacitor. Okay, so I hope I was able to make you understand this paragraph. Okay, like this video if this was helpful for you. Okay, if you find any mistake or you didn't understand anything, you can comment on the comment section. Okay, and like this video, share with your friends, subscribe to my channel. Okay, thanks for watching.